Hot dog teammates, it's Mr. Nanini coming to you with the solution for FRQ9. I gotta fess up. A friend of mine did this, sent it to me, and said this is great. So I used it, and I didn't solve it until this morning. So we're gonna look at this as a learning experience. When I assess your product, I'll keep that fully in mind. So follow along. I think we're gonna learn a lot together on this one. So you're given a circuit, you've got 3 switches, 1, 2, 3. The assumption you had to infer, and it wasn't very clear, that resistor 1, resistor 2 were with switch 1 and switch 2. So that wasn't terribly clear. Hopefully you figured that out. So initially, we're going to attack this one. We want to know what the voltage drop is there. So to get the voltage drop, we're going to have to look at the current times the resistance. And so, but there's some ciphering that has to go on, and that's okay. Up here, I think this is worth doing. We looked at this on the one from Friday. We had a very similar in terms of parallel resistors in parallel with this. RR, so 1 over R gives you 2 over R. Right? It's got a common denominator. 1 over R plus 1 over R is 2 over R. And you're going to flip it. That causes people a lot of frustration on that. But it's just like you're adding. So it's just like you had, so I don't know how to do, it's just like you had 1 over 2. Nah, it's gonna kind of lead you down the wrong way. Yeah, let's look at it. 1 over 2, like say you had 2 ohm, 2 ohm, you do 1 over 2 plus 1 over 2, you get 2 over 2, don't you? And it's the same thing here. Right, 1 over R plus 1 over R is common denominator, 2 over R, you flip it, you got R over 2. And I think that alone, I think, is worth doing this. Now, I hope this is all going to make sense. And you know how I feel about trust. And I don't want you to think I popped a sneaker on you. I should have reviewed this a little more. It looked good. It looked good till I started solving it. This part's not hard, right? So if you've got a resistance of R, I think I wrote it here. If you've got a resistance of R here and a resistance of half R there, that means that 2/3 of your voltage drop is going to happen there by voltage is current times R. Current's going to split our voltage because this is twice the resistance. It's going to have twice the voltage drop. Right, because our current's going to pass through. It's going to split, no big deal. But we're looking at our total current change in V over R, and so that voltage drop by Ohm's law is going to be 2/3. Send me a note if that doesn't make sense. I think you should be able to reason through that. Switch. 3 is closed. Immediately after, will the reading the voltmeter increase, decrease, or remain the same? This is tricky. So again, we're going to approach this as a learning situation. Technically, the current is going to take the path of least resistance. If we treat this truly, oops, you can't see. If we treat this truly as a ideal capacitor, no resistance, your current's going to bypass all this. But you're still going to get voltage through there. And so you're still going to have a voltage drop. And I hope that makes sense. I don't know that we've tackled a problem like this before, but I think it's okay. Does it make sense? So you're still going to get a voltage drop. because your voltage is still going to split. So because you get that voltage drop, and because your current is really is gonna bypass, it's a little tricky, but I think you can reason through that the resistance would decrease that way. I hope I'm making sense. I really am. I'm wanting to instill you with confidence, and I'm afraid I may not be achieving that. So again, you still get voltage down all three, but your current's all going to go this way, and so these are going to get bypassed, and so your overall resistance decreases. Your original resistance is going to be up here. It's going to be R plus half R, which is 3/2 R. You put this in though, it's going to bypass, and your resistance ends up R. So the reading in the resistance decreases, thus the current's going to increase, thus the voltmeter is going to show a greater increase. The only place you're going to lose voltage really is there, and I hope that makes sense. Ask me if not. So it has to, and here's where, we're really kind of bridging second year stuff here. If all the voltage dropped here, this would never charge, would it? So there's some funky physics going on, and I'll leave it go at that. I would just try to reason through this. We're not going to try and solve it numerically. Here's where I was not happy with this. You had to make an assumption here that this is current 1, current 2, current 3. And because of that, right, so you could have something different. You could have like a current 4 here, where current 1, 2, and 3 would add up to 4. But this would be incorrect, right? Because 1 and 2 are not going to add to that. You're gonna have some current like this, and it's go 1, 2, 3, like that. So again, yeah, worth a discussion. Kirchhoff loop rule. So you had the reason that this is I, and this is I1, this is I2. And the problem with that is you've got, you can't see, I'm just really not having a good day here. You can have a loop like this, and you can have a loop like this, and you can have a loop like this, but all three of those resistors aren't on the same loop. So that what makes this one wrong as well. Coming to the capacitor, this is a little tricky too. So again, I'm approaching this as a learning experience. So copper isn't a dielectric. And so there's not going to be any increase to your capacitance. I don't want you to fret on that. I think it's nice to know, and now you know. Because there's no change in voltage between the plates, right? The only difference, so your battery's hooked up. The potential difference is going to be based on that battery, setting the difference. Because there's no change in voltage, there's no difference in potential. So that's all I gotta say about that. This is a good teaching point too. We haven't gotten to this. There's no E field inside the block. What happens there is that the material in the copper is going to polarize. And if you look in Walker, am I even on the, yeah. If you look in Walker in the dielectric, it's going to show you how that polarizes. So that's worth a discussion. So this was worth a discussion. I hope that's okay. I hope that's okay. Don't fret. This was probably more complex than I intended it to be. It sure looked good. I should learn after 5 years to solve the darn problem first. All right, teammates. That's all I got. Talk to you soon.